There is also magnetism associated with the electron's spin angular momentum. For orbital angular momentum, the total momentum was the square root of L plus 1, times h bar. For the spin angular momentum, we replace these L's by S's, the spin quantum number. So the total spin angular momentum is simply the square root of S times S plus 1 times h bar. Now, in the case of spin, the spin for a particular particle is always the same. So for an electron, it's always 1/2. The same goes for protons and neutrons, which means this total spin angular momentum is just the square root of 1/2 times 1/2 plus 1 times h bar. In other words, it's always 0.866 h bar. You can look at that and find that it is also the square root of 3 over 2 h bar. As in the case of orbital angular momentum, a spin angular momentum is associated with a magnetic dipole moment. The formula is very similar. You would probably expect that we replace orbital angular momentum with spin angular momentum, which we do. The part you would not guess is that the factor of 2 here on the bottom disappears. It turns out that spin angular momentum matters more than orbital angular momentum when it comes to magnetism. There's no easy way to show that. It comes from the properties of spin, and that's above the level of this class. As a result of this, the total spin magnetic dipole moment is just E over m times the square root of S plus 1, times h bar. But as in the case of orbital angular momentum, it's very difficult to measure the total dipole moment. What we can measure is the effect of the component of the dipole moment along one particular direction, which we will call the z direction, and generally that is the direction of some magnetic field that the magnetic dipole is interacting with. So, the component of spin angular momentum along a given axis is just ms, the magnetic quantum number for spin, times h bar, and then the magnetic dipole moment component along that direction is just -2 ms times the Bohr magneton. The 2 comes because we didn't have the factor of 1/2 here. So here we have a picture showing the 2 possible orientations for spin angular momentum and their corresponding magnetic dipole moments. Notice they're opposite in direction from the spin because the electron is negative. The total magnitude of the spin angular momentum is always square root of 3 over 2 h bar, but the component along the z-axis is either plus 1/2 h bar or minus 1/2 h bar.